Hi, and welcome to today's session on Pragmatic Python with Eugene Huang. This meetup is jointly hosted between UpSkill ML, a meetup focused on empowering data science and ML professionals, Data Education DC, a meetup dedicated to democratizing data science, and in collaboration with Deep Learning Adventures, a meetup focused on positive change through deep learning. In today's session, Eugene will be going over part one of his Pragmatic Python tutorial that spans intermediate and advanced concepts in Python programming. Eugene is a talented data scientist who works at a Fortune 100 company. He is a self-taught programmer boasting a number of certifications and accolades, including a 4-time hackathon winner. He is a certified Google Cloud professional and is an open source contributor to Dask. Eugene is a graduate of UC Berkeley, where he majored in statistics and economics. With that said, let's hear from Eugene.
So welcome to Advanced Python, Code Like a Pro with Pragmatic Python. And as Josh already mentioned, I'm not a computer science major. I don't have a typical academic track in computer science. To update my bio, I actually took 2 CS classes. I took one in C, got a B+. Took one in R, got a B+. So what does this B+ student have to tell you today? Huh? My experience in Python started really when I went to coding bootcamp about 5 years ago. So mostly self-taught, not academic, so you won't see me do problems like this one showed on screen, horse mask. This one's like a recursion with complicated diagram with a lambda thrown on top of that. We won't do these academic problems. Like if you do C, they'll do like, oh, variable plus plus or plus plus variable, and do a for loop and ask, what is the status of this variable at the end of this loop? And you're like, I have no idea. I don't know what the plus plus means or the star star things. You're referencing whatever. What I'm here to show you today is how cool Python can be that's readable, extendable, and fun. So why should you listen to me? Or what's my credentials? As Josh mentioned, I'm certified in data engineering, so I can do both data science, data engineering, blockchain certified developer in decentralized apps, 4-time hackathon winner, distributed computing specialist. My interest is distributed computing, where I ETL'd 150 terabytes data on actually just one machine. I've also ran a distributed graph partitioning algorithm that I wrote by myself to distribute across 62 machines. Contributor to Dask, and I wrote my own Spark-like engine before I knew the existence of Spark. So, what are we going to do today? We're going to learn Python the easy way, right? Because what we have here on the left side is Zed Shah. He wrote a book called Learn Python the Hard Way. We won't do it the hard way. We'll do it the easy way. We'll do it the fun way. And on the right side, we have David Beasley, open source contributor to projects that called Curio, which is like async.io. He created, I think, the paper. He wrote a paper 15 years ago that helped create exception handling in Python. So he's been in the community for 20 years. He created a course called Practical Python Programming, charges $2,500. He also created another course called Advanced Python Mastery, charges $2,750. But you're going to learn all of that for free, the easy way. All right, so before I get into that, I want to explain why I wrote this tutorial. I wrote this tutorial based on the way how I wanted to learn Python myself. The reason was when I was an intern 5 years ago, I was programming in R at the time, and also I was not that great in Python. And a senior engineer said, "Oh, just use a decorator." And I heard, "Well, decorator? Is that something you decorate your tree, your house? Well, what is a decorator?" And I was basically too embarrassed to ask what a decorator was. And they also said, "Oh, just submit a PR." I had no idea what a PR was. I didn't know it stood for pull request. So I thought it was like PR. It's like, oh, that must be press release or something like that. So I was basically too embarrassed to ask these questions. So today I'm going to share with you all the cool tricks in Python that perhaps you're too embarrassed to ask about, or you were just too busy to learn about. So please join me in the matrix and join me in the code. So today, this is it. This is all my slides. That's it. What we're going to do is that if you join, so I have my code on GitHub, but there's a tool called mybinder.org that allows you to run code in your browser for free. So we're going to go over the first notebook called Pragmatic Python today. So please join me at this first link you see here. I'll also put it in the chat. There you go. So you guys should have it in chat now. So as this loads up, I hope everyone can join me. If you guys need the link, please ask me, or look at this chat message. But basically, mybinder.org allows you to automatically clone any repo, set up the dependencies, requirements.txt and so on, and run the code in the browser for free. And hopefully, we'll see if we can overwhelm mybinder.org today. Well, while that's loading, let me show you a brief overview of what we'll be learning today. Katrina? So what we can go over today is that we could code like a pro. There could be many multiple motivations for learning Python, but at a high level, Python offers multiple styles, the multi-paradigm approach. There's pragmatic Python, there's procedural Python, there's object-oriented Python, there's functional Python, high-performance Python, async I/O, event-driven, pedantic Python. And basically, I wrote a notebook for every single deep dive in Python. So there's 6 notebooks here. Each one of them is quite dense, but we're going to go over the first one. First notebook. So we're going to go over pragmatic Python. So here we go. So Python fundamentally is a multi-paradigm language. It takes the best out of different languages and put them all together in one programming language with batteries included, right? So we're going to have a first class look at object-oriented programming and functional programming today, and what we could do with functions. So quickly, let me walk you over the highlight of what we'll go over today. We're going to do some warm-ups with enumerate zip, ticks, ternary operators, list comprehensions, try except, so on. Quickly overview the practical aspects of object-oriented programming, and also give an overview of the practical aspects of functional programming. Talk about generators and lazy iterators. We'll see this thing called star args and star quargs. Cover decorators, and some helpful libraries in Python syntax and so on. So this is an ambitious goal. We'll see how far we can get today. So with no further ado, let's go over pragmatic Python. So let's go over some quick warm-ups. If you're fairly new to Python or came from a different language, you'll see that Python has different ways to do things that you might not be accustomed to. For example, in C or Java or R. Let's say I want to go through a string or some iterable or some container how can I get both the elements of the iterable as well as the index of the iterable? So in other languages, you would basically do this, like in C or Java. It's been a while, but I think you might do that in R as well. But in Python, you could just iterate over the elements of iterable and get that immediately. And then you could stick on enumerate. So if you want to enumerate over the string, you get the index and character as the tuple that you're looping over, and print that out. And if you want to start off from 1 instead of 0, or some other starting index, you would put 1 here. And that's all there is. To enumerate. So I'm going to quickly go over these warm-ups because most of you are familiar with it. Let's take another useful tool called zip. Basically, if you want to if you want to go over 2 iterables simultaneously, you could use zip, and you could even do that for n arguments. So you could do it for 3 and more iterable objects. And what it will do is it stops at the shortest one. So like here, it's zipping through this string in range 42, so it stops at the shortest one. There's something called zip longest, where you can zip to the longest iterable, and then you could go all the way from 0 to 41 in this case, and then you would have to do the fill in for the elements that are not long enough. So there's zip longest as well, but that's less often used. So dictionaries, let's go over quickly dictionaries. There are different ways to construct a dictionary. Dictionaries can be created with a dictionary literal. It can be created with a dictionary over iterables. It can be created with dictionary with keyword arguments. It can be created with a dictionary comparison. And this one is an interesting one that most people aren't aware of. But you can create one from dictionary.fromKeys. This is a class method that allows you to input the key names and then fill in the values, which they will all be the same, which corresponds with this one. And from the lesson above, you get to use enumerate as well as zip. So there's multiple ways to use dictionaries. Let's see. The quick thing is that for dictionary with a key that does not exist, it'll give you a key error, right? But a safe way to do it, to always run successfully, use the get method. If the key does not exist, then return none. Otherwise, get the value corresponding to the key. But if you want to get a default value, so suppose that the key does not exist in the dictionary, but you don't want none, then you can pass in a second argument that specifies what will be the default value if the key does not exist in the dictionary. So you get this one. Certain destructive or mutative methods is pop. You can also pop with a default arg such that if the key does not exist in the dictionary, then pop this default value. And so on. I'm going to skip over this, but these are just nice tools that you do with dictionaries. This one's really interesting. It's called ternary operator or conditional expression. It's expression because if you're familiar with C or R, this is how you would do it in those two languages. And this is how you would do it in R for vectorized condition. But in Python, instead of writing these 4 lines, you can write it with this one line. This actually comes from, I believe, math or MATLAB syntax. So this was a new diction in Python 2, I believe. So let me go to list comprehensions. This is like one of the last fundamental things for, let's say, beginner to intermediate Python. So in list comprehensions, you could create a list using a basically a generator expression. So don't do this, do this. So here we have creating a list, then appending to it using for loop. So that's 3 lines, but that can be done identically with 1 line. But not only that, you could stick in any arbitrary functions or expressions into your list comprehension. So if you wanted to do absolute value, that's how you create this list. Or if you want to do mutations to a string, you could do this. So, and like previously, there's if you want to zip over multiple elements or enumerate over an interval, that's possible with list comprehension. List comprehension can also do filtering syntax. So here I just want to get the odd numbers. So instead of these 4 lines, I could just simplify that with 1 line. So list comprehensions can emulate map and filter simultaneously. And you could also stick a ternary operator inside the list comprehension itself. So for every number in range 10, determine if it's even or odd. So this is, in this case, we have a ternary operator, we have a filtering condition and the ternary operator here. So basically, you could think of any complicated thing you technically can do in a list comprehension as long as it's a 1-line expression. You can even do a nested list comprehension where you have a list inside a list, or you could unravel a list. So given an input list, flatten it out. So basically, list comprehensions are extremely expressive things that simplify your workflow with 1 line. So can you do a double list comprehension with a nested list comprehension that has multiple iterables with a filtering condition that has the expression of a ternary operator? Yes, that is possible, but please don't do it. In practice, what you should do with list comprehension is to have a map expression and possibly a filtering condition. And you can use this type of comprehension technique for dictionaries, sets, tuples, and just the generator itself. In this case, let's also go to the final section in this warm-ups. So try except. So in other languages, exceptions are not a common part of the runtime, like C or R. So you're more cautious. You check the types or check the necessary conditions before you run the operation. Well, in Python, you can throw caution to the wind because there's 2 competing paradigms in Python style that you could change based on different use cases. There's look before leap. So it's very similar to a statically typed language. We're checking the conditions, the types, to make sure that things are correct. Checking if a key is in your dictionary, that sort of thing. You want to be careful before you run an operation. The other option is to ask for forgiveness. It's easier to ask for forgiveness than permission. So just try it out. Just try it out. And what that gives you is that fatal exceptions in Python are much rarer because Python allows you to anticipate exceptions and handle them on the fly. So in other languages, if you did 1 divided by 0, you just get like a 0 division error and just error out, terminate, die. And that is true in Python unless you put a try except block. So once you have a try except block, then when you hit an exception, you could intervene in that specific exception types and then continue along as if nothing had happened. So this is just a quick primer over try except, and that is a quick primer of maybe beginner to intermediate Python. This is stuff that most of you probably already know. So let's get to the juicier stuff. Let's get to the advanced Python. Let's go over practical object-oriented Python. So here's some lingo. A class is a blueprint or definition of creating an object. Another synonym for class is type. Object is an instance of a class. It's a manifestation of your blueprint. And creating an instance from a class is called instantiation. But sometimes people use the word object in a very loose manner, and that they say everything in Python is object. That's actually technically true, because even a class is an object. Even a function is an object. Even a meta class is an object. Even the object itself is an object. So what they mean when they say everything's object is that anything that's assignable, storable, is technically an object. So that's a more broader or looser interpretation of what an object is. So what is a method? A method is just a function you put inside of a class. That's all it is. That's just a fancy word for a function. There's some properties that are unique to functions, to methods. Like the method has access to the class. So there is a hidden method on top of the method object that you could find, like class name, file name, and so on. But those are very technical details that are not too important. And lastly, an attribute is basically data inside a class. That's basically it. So in short, Python instances objects have four things. It's got a class name, it's got attributes, which are, you can think of the noun as the data, and methods are the actions or the verbs that manipulate the data. And there's a unique identity for every instance of the object while the object is still alive. But let's go through some examples, right? Let's go through what the methods of objects are. We have an instance method, which is what we use most of the time. We have a class method that we use less frequently, and there's a static method that we use very rarely at all. So let's take a look at this class. So I create a class called myClass with this class attribute 42. This is not a instance attribute. This is a class attribute. And then I create a in this method, when called, will create an instance attribute and then return it to me. And then I have this class method and the static method. So basically I have a method of each. Instance method, class method, and static method with a class attribute and instance attribute. So let's take a look at what this actually does. So we take a look at the instance method. And the instance method just sets this instance attribute and also returns the instance attribute. It's kind of like a setter and getter at the same time. So this one works on instance, but it does not work on the class. This class does not have this, it has a method, but it does not have the correct arguments. So this 10 corresponds with this line, but this one corresponds with a traceback. So basically it's saying that when you call the class and then the method, it's looking for the self argument, but it doesn't see it. So if you did so when you call a class method or an instance method, it's actually doing this. It's actually calling the class, then the method, then the first argument itself. So if you pass in an instance, then you're going to be totally fine. So let's say my instance attribute is currently 10. I'm going to set that to 13. And now that's 13. So when you call a class method, or when you call a method, the first argument is self, which is the object itself, and then whatever other arguments is. So if you wanted to call the method, the instance method from the class itself, you actually can do that, and it would look like this. So that's a cool trick that most people aren't aware of, but it's possible to use an instance method called at the class level where you pass in the instance itself. But you can just call it the instance method. In this case, I'm going to set the, so this one is just the instance calling the instance method. Nothing special there. Now I'm going to create a different instance and then take a look at and set its attribute there. So then the point here is that each instance has its own instance attributes. Right? Like each instance has its own instance attributes. And I can set them at will. But an instance actually can communicate to, you can consider its parent, its class, its type. And so if you want to look at an instance, you can automatically connect to the instances, the classes, methods, and attributes. So in this case, I'm using the instance to call the class method. I'm also using the class to call the class method. Both of them are valid styles. Probably this one is probably more preferred, but both of them are valid. So let's take a look. So my class is calling this class method. And so that's calling this method. So you notice there's a n% class method. So we'll go over that later. But basically, this is how the syntax to convert an instance method to a class method. And notice that the first argument is no longer self. It's class. And then I'm referring to a class here. I'm referring to my attribute here, my class attribute, which is just 42. So down here, when I'm calling the instance's class method, it could pull out the class attribute, and it's the same for if you use the class to call the class method to get the class attribute. So both class and instance have access to class methods and class attributes. And class attributes are, so it doesn't matter if you're calling it from my instance 1 or my instance 2. Both instances of the class have access to class method and class attributes. In fact, the class attribute can be updated, and that'll be visible by all instances. So I'm going to update my class attribute from 42 to 43, and that will be automatically visible to all instances. So my instance 1 and my instance 2 now is reflected with 43. And if I run it again, it will also say 44. So there is only, so each instance has its own instance attributes, which are separate from other instances. So my instance 1 and my instance 2 has its own separate and independent instance attributes, but they both connect to the class's instance methods and instance attributes. So that is shared. It's like, I guess, teleportation. And lastly, there's the static method. This one's used very rarely. But basically, you could attach a regular function to a class or instance without it really being a method. So notice in this case, there is no, for converting an instance method to a static method is basically just a regular function. Pretend as if this method has no understanding of either the instance or the class. So this method cannot do self dot whatever, and it cannot do class dot whatever, because this static method has no understanding of the instance or the class. So the arguments are just regular arguments. It has no self and no class. So in this case, it's a simple method. It's basically a static method is just a regular function, and in this case it was just the adder. So I just add 1 and 2. Notice that I could call that method from both my instance and my class. So that is a quick overview of object-oriented programming for Python. In fact, there is another notebook that delves very deeply into instance dictionaries, how to overwrite some of the Dunder magic methods, how to create your own context manager. So object-oriented Python can go much deeper, and but for now, that's the overview of object-oriented Python for this notebook. Does anyone have any questions?
Great session, Eugene. I had a question. When would you use, I know you mentioned that instance method is the majority of the time where you use help. Do you know any examples where you use a class method or a static method instead?
All right, that's a great question. Let me answer the second part of your question. When would you use a static method? So a static method is basically a helper function that you wanted to pair with this class for some reason. So like instead of just defining this, so like as a static method, that's literally copy and pasting. That's effectively what it is. It's really just a regular function, right? It's got no self, it's got no class. So it's literally copy and paste, you stick it into class or choose not to stick in class. So basically it's just a helper function that you might often use with the class. So if this class often does adding for some reason, you could just stick it in as a method. But you're also preventing the user from inspecting the instance itself or inspecting the attribute itself or the class itself. So in some sense, a static method is almost like encapsulation or privacy to protect someone from using attributes of the instance or class. And for your first question, for first half of your question, yes, when is class method helpful? A class method is helpful. One way is it's an alternative constructor. So for example, for dictionaries, right? You could do a dictionary literal, right? But suppose that you want an alternative constructor, and you don't want to use the typical init. So let's say I had an init here, blah 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 here, right? And in this case, dict from keys, right? Suppose that I had some dict class. I'm just gonna pseudocode, and suppose this is the implementation for like Python's dictionary class, right? But I could also create effectively the class method to say if I wanted dictionaries with a certain the keys to be different, but the values to be the same, that's an alternative constructor. I'm constructing the instance without using the init directly. I'm using an alternative way to create an instance of the class. So the from keys method, if I were to implement dict's from keys method, will look like this. So that will be the effective implementation of the from keys method, which is alternative constructor. So if I just did range 10, but I want the values to be my favorite value, that's what it would look like. So that's what class methods are. So basically, the class method is, in some sense, less expressive than the original constructor, but it's like a convenience function in that it does some things already for you. So that would be a use case for a class method.
Thank you.
Does anyone have any other questions about OOP? So before we get to the next section,
Quick question.
yes.
I joined a bit late. Did you talk about deriving classes?
Like inheritance?
Yeah, like another part of object-oriented programming.
That's a great question. In this notebook, I don't delve into inheritance, but I do in the object-oriented notebook with inheritance, super, mixins, alternative constructors, and some other tricks.
Thank you. That's great.
So all your questions are there. Fluent interfaces and so on, properties. So there's a lot of cool things you do with object-oriented programming. I think most people use Python, or at least in data science, they use it with some object-oriented programming as the proclivity event. So there's definitely more to object-oriented programming than I'll show in this demonstration of Pragmatic Python for today. Is there any other questions about object-oriented programming?
I'll ask another quick one. For static methods, are there restrictions on what you can invoke or what you can access?
That's a good question. Static methods are truly just like regular functions that know nothing about the instance at all. But so in this case, the static method, right? It's literally copy and paste, right? So it has no self and has no class. So there's no real restrictions. If hypothetically you said you want to have ability to access instance, what you could do if you want is you can inject it after the fact. So if you inject the instance like this, this is a horrible idea. Instance dot my instance method. Like if you want to inject it back into it, that's actually possible. So now if I create an instance of this class and then call this, let me just call it directly from the class itself. I need an instance of this class first. So I'm going to say instance. And my instance has, let's say I'm going to set this instance value to 13. So it's currently 13, right? If I now call this class, and if I use a static method, right, and I kind of injected my instance back in, now that instance is now mutated, successful. So like, if you wanted to give the static method understanding the class or instance, it's possible. So for example, if I could do this with class too, right? I can inject the class. I'm going to do class, and then I'm going to call the class attribute and do that, right? So in that case, my class attribute is 42. But now I'm going to take an instance of that class, this instance. I'm going to mutate the class attribute from the instance. Kind of strange, but it's possible. Not callable. Let me just do this. So now I've mutated my class attribute from an instance. So 42 changed to 43. So it's possible to give a static method understanding of an instance or class, or even other classes. Right? You can pass in anything into these arguments. It's just that you typically would not pass in self or class in a static method. So is there any other questions before we move on to our next section in practical functional programming?
Yeah, I wanted to ask a question for the. This is going back to the almost start the instance method. One, I can see it's cool for attribute for instances. What else would we use it for, or is it strictly for that purpose?
So did you ask about the class method or the static method?
Uh,
Or can you ask your question again?
yeah, the very first method on the my class,
This
my
one.
instance method. Yeah. So the function of that, I'm trying to see if there is a broader function of that, or is it just strictly to update an attribute for that instance?
Good question. It's strictly to update or an attribute or call other methods of only that instance, because you're passing the keyword self, and self is an instance. So you're doing self dot, attribute, or self dot some method, self dot, whatever. So it's actually really that self, that instance. In fact, self is actually not a keyword. Notice it has no context highlighting. You could literally put the word banana, and it would still work. Self is not a magic word. In fact, you can name some object self, and self dot class method, and it would still work because you get the uh, call the class method. So like self is not a special keyword. It's just by convention. And so when you have an instance method, you're really just mutating typically the instance attribute, getting an attribute, setting an attribute, calling method on it. If you were really fancy, you could convert this instance method to a class method. And what you would do is how would you do that? What you would do is you get the type of this instance and then call a class method or static method. So let me give you a quick example. See, for example, in this instance, I'm going to start mutating the class attribute. All right, I'm going to do some magic here. So in this so the class attribute says 42, right? I'm going to change it to 43. So I'm going to pass in the self, the instance, but get the class of it, which will be my class, and then set the attribute here to be this. So like, you're right. Like typically we think of it instance method as mutating an instance, but it really has access to everything. It has access to the class itself. So the class has the class method currently 42. I'm going to set that to 43 from the instance. So that can be done if you want to. Does that answer your question?
Yes, thank you.
Does anyone have any other questions? So in that case, I had a request from Josh to give us a brief break, but let's take a quick brief break, and then once we come back, we'll tackle practical functional programming. So Josh, you could take it away.
Thanks, Eugene. We'll take a brief break for 1 or 2 minutes and allow people to stretch their legs. And when we come back, we'll jump into the functional programming piece.
All right, guys, it's 7:01, so let's try to see how much we go through this notebook. If anyone has any questions that they just thought of OOP, object-oriented programming, feel free to ask. Otherwise, we'll go into functional programming. So before we do that, if you have any questions, please ask. Feel free to ask me. Well, if there's no questions for OOP, or we could, if you have that question and want to save it to then, feel free to keep it in your mind or write it down. So let's take a quick dive into practical functional programming. So, suppose you live in a world where you don't use classes. How can you do anything, right? The value of classes or object-oriented programming is such that you can contain both your data and the functions together in the same place. You're binding data and code together in objects. But how would you do that in a functional programming style? You don't have objects anymore. You don't have classes. You don't have methods anymore. You don't have instance methods. You don't have class methods. Well, all you have is static methods, which are basically functions in the first place. So, what does functional programming excel at? It excels at decoupling. It has an antithetical paradigm. Instead of coupling data and code, you're specifically decoupling it. And the reason is that in object-oriented programming, you have these instances, right? And it's messy. For example, everything in Python is an object. Even the number 1 is an object, right? Type. Something like what type? So it's int, right? So integers have methods. That's kind of strange. So these primitive objects, even these primitive objects like numbers and bools, you think that's all there is to them. There's nothing else. But they are objects. So the problem is that from a functional programming standpoint, objects are messy. Why are they messy? It's because you can inspect them, you could change them, you could fiddle with them. And functional programming says, I'm not going to allow you to fiddle with any of these things. I'm just going to keep my functions separate, my data separate, and when I want to combine them, I'll mix them for a short period of time, and that's it. I don't want you to touch the instance attributes. I don't want you to touch class attributes and so on. So functional programming style would use primarily map, filter, and reduce. And they don't have for loops. So no classes, no for loops. Oh my gosh, what type of crazy world are we in? Well, we're in the twilight zone. We're in the functional programming zone. So let me go over quickly map, filter, and reduce. And before we do that, we have to first know what a lambda function is, or also called anonymous function. So anonymous functions, or lambda functions, give you a quick way to define just a one-line function. The expressiveness of a one-line function is limited to only expression. So no statements, so you can't delete, you can't assign, you can't have context manager. So those are the rules. So you're playing with this limited set of rules in a lambda function. So quickly, what is lambda used for? Lambda functions are good for sorting. So if I wanted to sort a dictionary, or sorry, a list on the first element, I would uh, just use sorted. So if I just want to sort on the first element thing, I just do this, right? So like if I did change this to go reverse, there we go. So just as 1, 2, 3, right? But if I want to sort on the second element, I would use a lambda. And the lambda says that given the element, what should I extract that value to be? I'm extracting the second element. And then sorted says, based on that comparison of the second element, sort it. So I'm sorting by x here, y, and z. So that's a simple lambda expression. Lambdas are also used in pandas. Apply. So given this data frame, just even numbers 2, 4, 6, 8, I want to create a extra column that has the elements squared. So the lambda function is square that element, so it's 4, 16, 36, 64, right? So the construct of the lambda is lambda, which is essentially a def, then your arguments. So like lambda, you can have multiple arguments, just like a def. And just think of this as your body of the function, but it has to be a single expression. So no assignments, can't do that. No context managers, right? That type of stuff. And no easy loops inside the lambda expression, because a lambda expression is just an expression. That's what a lambda function is. Really, it's really just an expression. So now this is interesting. Okay, so let's get to this thing. So now we're doing functional programming. We have map, we have filter, we got reduce. This is it looks like a basically callback hell. Like if you were doing some building websites, this is kind of what it looked like if you use callbacks instead of like asynchronous programming. But let's take a look at let's look at the innermost first, right? So what are we doing here? We have the numbers 0 through 9. We're mapping it, so we're just applying a function which multiplies by 3. So 0 through 9 becomes 0, or 9 times 3, so that's like 0, 3, 6, 9, 11, 12, and so on. Then this filter basically only keeps the odd numbers. So I'm going to filter. So like if I did number like 6, right? I'm going to modulo 2 and it gives me 0. So 0 is a falsy value. So that's actually filtered out. But if I do 9 modulo 2, then I get 1. So that's a truthy value. So I just basically get all the odd numbers here. And finally, I'm reducing here. So reduce is basically a for loop that is an accumulator. So I'm just adding all the odd numbers together. And at the end, you get another odd number. Right. So basically, this map is basically a for loop that is multiplying all the numbers by 3. This filter is a for loop that only keeps the numbers that are odd, and this reduce is a for loop, but it's not doing. You're not getting element wise out of it. You're getting one element out of it because it's doing for loop, but it's accumulator. It's iteratively adding the numbers together. So you can do the same thing with list comprehension. So list comprehension can emulate a map and filtering operation perfectly, because here is the mapping operation, multiply everything with 3, and here is the filtering condition. But it cannot do, a list comprehension cannot do a accumulation natively. So you just do accumulator here, and then you're looping through the elements and getting this summation. So in functional programming, it would look like this. In procedural programming, it would look like this. Think about this. Yeah, so this is how you do for loops in functional programming. There are no for loops here, but it emulates a for loop exactly. So for loops in procedural programming, no for loops in functional programming. You would have map, filter, and reduce. So quick takeaway here, just a minor point, is that you could actually name your Lambda function if you want. So like if you do, Lambda x, y, and just and lambdas can also contain default args. So they behave naturally like any regular function definition, but they're just still one-line expressions, and you could technically assign it to some variable. So and you could call it like a regular function. So like if you look at the function calls here, you could actually not distinguish between if it was like a regular function or if it's a lambda function. And here using a reduce, given a list from 0 to 9, I'm just going to add up all the numbers. And you get 45. And reduce has a third argument that basically can start you out. So if I wanted to start, like essentially prepend a value to this list, I would put it here. So for like 10. So I put 10 here, they'll say 55 here. So basically, if I had this accumulator, let's say accumulator equals 0 or something like that, for I in range 10, summer accumulator, I accumulator. Basically, this extra argument here initializes the accumulator what it would be. So that is an optional third argument for reduce. So if you said, 100 here, that would be equivalent in the for loop as 100 here. So you get 145 and 145 here. So you can also initialize the reduce as well. So for a lambda expression, because it's just a single one expression, you can't do the following. You can't create a multi-line body of this function. So that cannot be done. But what you do to get around the fact is that you create a tuple, or in this case, a list. So it's returning a list right here. So if you can't do it in one expression, you can stick multiple expressions. Let's say x plus 1, or x plus y, and x times y. Those are two expressions. We stick that in a list or a tuple, and then it becomes one, you can say, composite expression that comes out. So like that's how you can get around the one expression rule in lambda. So for example, you could do this sum x, y. You could do float x, and you could do absolute value of y. So like you could technically get around the rule of one expression in a lambda. So this is how you can make one lambda expression do multiple calculations, multiple operations. So the next thing is that let's go into lazy operations, lazy transformations. And what's really cool about lazy operations is that they defer computation until you actually need the result. And that gives you two main benefits. Because it saves you memory, because you don't have to materialize the entire object in memory, and you could potentially save some runtime. And I'll show you in instances which it saves runtime. But for example, let's quickly go over just range. Range in Python 3 is a range object, and it occupies virtually no memory. It actually occupies constant memory, O1 memory, because what it does is it stores really 4 objects. It stores the starting element, it stores um, the end element, and it stores the skip level, and it also stores what element you're currently in within this range object. So if you take a look, it's this range. So a range object only stores 4 things in memory, which is O1 constant time. So it's perfectly scalable. Um, but that's in Python 3. Python 2 does not have the range Python 2 actually generates a list. So it takes a lot of memory. So like this line of code in Python 2 would fail because it would just require too much memory. And it would also take too long to ever compute. So it's impossible because range of like a trillion or quadrillion would just take up too much time in Python 2. But in Python 3, you can do this with constant memory. The equivalent of Python 3's range in Python 2 is X range. But in the advent of Python 3, a lot of those things that you prefix X with, X range or certain iterators in Python 2, like enumerate, I think was also a generates a list, or zip generates a list in Python 2. But in Python 3, all those things have been converted into lazy iterables. So to show you that I'm not lying, that it really does store constant memory, right? Let's say I want a range of numbers from 0 through 8, even numbers, right? But then I do the same thing with 0 through 10, 100,000. So both of these objects in memory take only 48 bytes. So my guess is that each number takes maybe 12 bytes or something. I don't really know the internal implementation details, but it's really taking just constant memory. So even if you want to do range of this, it would still be 48 bytes. So what's the value of this here? The demonstration of this thing here is to show you saves memory. Lazy iterables save memory because you don't create the entire thing in memory. For example, if you just did range 10,000, right? Size of this would be substantially larger. So let's go to so map and filter in functional programming are lazy as well. They take constant memory. So if I want to do map of range 10, so I'm just multiplying each number by 2, I'm doubling it, I get this map object back, which is really a generator, effectively. And the memory is 64. So if I did range of, let's say 10 million or something like that, it'd still be 64 bytes in memory. So this is constant memory. So you could chain together multiple maps, filters, and have constant memory. So another cool thing about lazy iterators is that you don't consume all the elements of map and filter in one shot. You could do it piecemeal. You just get the next element, the next element, the next element, just like you would do in range. You don't need the full range. You don't need a list of like a billion elements. You could just consume 4i in range. So like get 0, get 1, get 2. So how do you get them? Like a generator, you just once you define your map or filter expression, to get the next element in that generator, you just click next. So next. So what happens when you run out? When a generator or a map or filter is exhausted, the generator will raise a stop iteration. In fact, that's how a for loop actually stops too. A for loop is only stopped when the elements of the iterable it's iterating over is exhausted, and then it naturally causes a stop iteration, raises the stop iteration in the for loop behind the scenes. So that's actually how even for loops are implemented. So this one corresponds to range 5. So you get numbers 0, 1, 2, 3, 4. So 0 times 2 is 0. 0 times 1 times 2 is 2. 2 times 2 is 4, and so on. So this one is 4 times 2 is 8. And then the final one is the stop iteration. So moving on, lazy objects are also chainable. So you get chain a map, then top of the map, right? I store it as this variable as doubled, and then doubled, I then filter doubled based on if modulo is of 3 is equal to 0. So basically, if it's a multiple of 3, keep it, otherwise discard it. So in that case, all the elements here would be divisible by 6. So when I print it out, I get still another lazy object. And what is the size of that object? Still 64. So like, it doesn't matter a microsecond. So this is 1 nanosecond, I think, is 1 millionth of a second. So like creating lazy objects is so. If you want to chain it together, that's what it would look like as a chain expression. But you could do this in one shot, in one line. So like this is kind of like callback style. So like and instantaneous creation, right? So in this case, let me compare and contrast a list comprehension with a lazy map and filter. So this is the list comprehension way of doing map and filter. So here's the mapping operation. As exactly as before, I'm going to multiply every element by 2. Then I'll keep only elements worth by 3, and then I'll multiply those elements by 3, by 2. So in this case, I'm creating a reified materialized list, and that will take some time because it's an actual object that occupies actual space in memory. So this list, if I were to print it out, well, it's quite large. I don't know how many elements there is, but it's quite large, right? It occupies 2.6 bytes, right? And but it's identical to this generator if I were to manifest it. So if I were to manifest that one, I should get the exact same result. Oh, I got perhaps a little larger, but basically the same thing. So creating a reified list takes time, takes 300 milliseconds. So that's like a third of a second, right? Because it's actually got to create this list, then derived off the list, create another list, and then create a third list. So there's actually 3 lists in memory, all of them taking variable amounts of RAM. So ON space complexity. So you have 3 lists, where this one is actually the largest one. But here in the functional style, so map and filter, all these things together is like 64 bytes of RAM. So this map object map generator is 64 bytes of RAM. This intermediate filter object is also 64 bytes of RAM. And the original map object is also 64 bytes of RAM. So altogether, they scale very well. It's basically constant time. So that gives you the RAM efficiency of using map and filter. So let's go to the second point of the what lazy operations do. The second one of lazy evaluation is to defer runtime. So you save runtime. And that's also useful if you never intend to consume the full list. For example, if you have a list of 1,000,000 objects, but in that function it returns before you get to the 1,000,000th element, right? You only go halfway through, right? You only consume half that list. Then you spend a lot of time creating that list if you were to manifest it into a full reified list of 1,000,000 objects. But if you use a generator or mapper or filter, and you only go through half of that list, then basically you saved half the time. So you're able to, so for list comprehension, you push the runtime in the beginning, to the front, the beginning. But when you use map or filter, you're able to amortize the runtime at each invocation of the next element in that generator. So if you don't use the entire list, or you don't use that entire generator, then you cut down the amount of time you're using. So that's deferring runtime not only defers runtime, but also can cut down on runtime if you terminate the loop prematurely. So time considerable. So let's go with reduce. So reduce is an accumulator operation that that's basically equivalent to for loop, but accumulates the results of your list together. So like, for example, you add all the elements in your list together, or you multiply all the elements in your list together. So reduce is actually non-lazy. This will actually return a real object back to you. So it returns this actual number. So this is the result of the reduce. So reduce is non-lazy. It will actually consume runtime. It will also consume a bit of RAM. It should consume fairly constant time memory because it's iterating over the elements of the object you already have here. So if this thing is like a list already, then this takes a lot of RAM, but the reduce doesn't. It's just iterating over it. If this is a generator, then reduce also doesn't take a lot of RAM, just takes constant RAM because it's looking at the current element and the next element. So reduce is when it takes two arguments, it's looking at the current value of the accumulator and the next element in your iterable, and then you do an operation, and the result of this expression becomes the next x, the next current state of the accumulator, and then the next element of the iterable, and so on. And so in this case, here's the case where here's a case where having a generator or map or filter has benefits over a typical list. Okay, let's try this out. So that's good. So this one takes 83 nanoseconds, so less than a millisecond, less than a millionth of a second. I think a nanosecond is like milliseconds 1,000th of a second, microsecond is a millionth of a second, and nanosecond is a billionth of a second. So this is 83 billionth of a second. This is 400, and this was that. So 83 millisecond nanosecond comes from using map and filter generators, so essentially instantaneously. And this is using a list, so it's creating a true list. That'll take a lot of RAM, and it's taking 473 milliseconds. So like literally at least 3 order of magnitudes slower than the generator expression. And the reason why is that I'm using zip, but I'm not zipping over, I'm zipping this long list with this very short list. So in this case, I don't need all of this list. I don't need a million objects. I only need the first 5 because that's what zip does. So in this case, you've basically wasted all this time creating these objects that won't be fully used. Whereas in a generator, I only am able to pick out the first 5 elements to zip along with range 5 and then generate the final list. So a generator and a full list comprehension can do the exact same thing, but a generator often has runtime and memory benefits. So both space and time complexity improvements in using map, filters, and generators. Does anyone have questions about functional programming so far?
I had one question. For the very first lambda expression, can you explain what the top one for the sorted as
Right there.
yeah, can you explain what the lambda function is doing there? I'm just trying to wrap my head around the indexing inside the function.
Sure. So first sorted basically takes an argument. This key argument is an argument of sort itself. And basically the key requires basically a function. There's other ways to do it, but for most users, the key argument of sorted takes a function. So you could take basically a regular function. So like if I were to define it like this, get second. That's effectively this. So basically, all I do is I pass into the key argument a function telling how I want to sort this iterable here. And in this case, I'm getting the second element in of the tuple. So z, y, and x. So let's say I want to get something interesting. Let's say I want to do this, right? I want to get 1, 2, 3. I'm getting the first element, right? 1, 2, 3. How can I reverse the sort? One way I could do is I just do reverse. And it also creates a generator, so it doesn't actually show it to me. So I have to do this. So that's one way to do it. But what's another way to do reverse sorting using a lambda expression? You stick a minus sign. There we go. I don't think it works for like strings though. So like if I want to do reverse, like instead of saying x, y, z, I want z, y, x. I think this is probably not going to work because you can't do a minus. Yeah, can't do that. But for numbers, for numerical values, the reverse of the increasing value is that you just take a negative sign, and then like 3 becomes -3, 2 becomes -2, and 1 becomes -1. So that's how you can reverse the sort using -i, using lambda. Does that answer your question?
Yes, thank you.
Sure thing. Does anyone else have any other questions?
Eugene, this is great. Can you tell us the difference between the percentage time and percentage time? I think you mentioned it somewhere in your notebook, but I didn't fully read it.
Oh, percentage time and percentage?
Yeah.
Percent and basic Python. This is pure Python. It's just modulo. In fact, it's actually, if you want to do floats, you could do this too. And basically, it just gives you the extra part. So the extra part of this division, you could say the remainder is just 0.5.
Yeah, I'm actually talking about the wall time and the CPU time.
Oh, I see.
Yeah, you have a difference between 1 and 2 percentages.
Yes. Thank you for the clarification. The 1%, these are not Python operations. These are Jupyter notebooks. They're also valid in IPython, but not pure Python itself. So 1 percentage sign is inline timer. So, range some massive numbers, and I'm going to say list. Oh, shit. That's it. So, basically, in one line, I could time this expression. But that's for one line. The percentage affects the entire cell. So you do like multiple. And it would run the entire cell. And you can even mix and match. So if you want, you could even stick a percent time in a cell percent time. And it would, the first one is probably the percent time. What I can do is just print. There we go. So the first one does represent the percent time. The second one is overall time of the entire cell. And there's a cool trick. These are called cell magic. So like not only that, that's just running the cell one time. But if you want to run it multiple times, you do time it, and it runs it multiple times. At least I think 3 times. So it's taking a while.
It gives you averages, right?
Yes. So I ran it. I think I ran it way more than 10 times. But yeah, it runs the entire. It runs that line multiple times and gives you the average. And you can also do it with the cell magic as well. Or if you want to apply it to the entire cell, I guess it truly runs it for 7 times. So and it'll tell you the average time and I guess the standard deviation.
Cool. Thank you.
No problem. Does anyone have any other questions?
Yes, Eugene. So in this example, can you for percentage time and percentage time? So can you give some practical use case of this function? Like why would we care about exact timing? Like certain things will take.
Sure, that's a great question. Let's say you have like a bunch of functions and it's super slow, right? And you have basically no idea where it's coming from, right? You can't figure out the trait. You could like run a runtime profiler, but it's like spits out some incomprehensible stuff, and you just need something quick and dirty, right? And you could do it iteratively. The notebook with the REPL, the notebooks, REPL, read, evaluate, print, loop, right? That's what the Jupyter notebook is good for: reading, evaluating, printing, and then repeat again, which is the loop. So if I were to do a function, like multiple functions, and I don't know where the bottleneck is, I stick to the percent time to try to figure out what is the bottleneck. And oftentimes it's actually, it's different than what you had imagined, right? Like one of the Zen of Python is, or I think from Tim Peters, is that premature optimization is the root of all evil. So if you had assumed like function 1 was very slow because you're doing a range over like a billion, right? You think, oh my gosh, my guess is that it's slow in function 1, but you don't know that, right? You don't know. That's your hypothesis, but how do you prove that hypothesis? you can falsify this hypothesis by actually running it through timer. See if it really is function 1, maybe it's function 2, because maybe function 2 has only like 10 elements, but it's hitting a database. And maybe the database connection is very slow. So even though that function 1 might look like it's the bottleneck, it actually could be function 2. And that's where percent time is very helpful.
Yeah. Thanks, this helps.
No problem. Does anyone have any other questions?
I have one question. You had an example where you were generating a range of numbers and then eventually you would do reduce and you had an answer 75. If we could go to that example.
Yeah.
So for the reduce, the syntax is a little bit peculiar. It almost feels like you need to have like a number and then another number and then the rest.
Yes.
And at each iteration, you need to take one of the numbers from the list that gets passed to it, right? Is it implicit here?
So the second argument of reduce is just a iterable. So it could be a list, it could be a tuple, it could be technically any iterable. It could be a string, it could be a dictionary, it could be a set, like reduce. Let's see. I mean, it could reduce anything. Let's do some horrible.
That's it. Got it. I just didn't see it, so it was actually a comma. Okay, thank you.
And there's also an optional third argument that you can put here that initializes the accumulator of the reduce as well. So like if you set the accumulator to 0, then it'll be 75. If you set the accumulator to start off with 100, then it'll say 175. And suppose your iterable is nothing, right? Like it's empty, right? That's when the default value would be helpful because there's no initial value. So you say, oh, this is my initial value. So if my iterable is empty, set, list, dictionary, tuple, string, I still can get a default value out of a reduce. Does that answer your question?
So the confusion was, so we're passing x and y. So technically y is the iterable, right? In the reduce, but we actually peeling off like an element and then passing the rest for the next iteration. So that's where my confusion was, so to speak.
Yeah.
You see what I'm asking? Because we're using the same name for two different things here.
Yeah, that's actually quite confusing. Y is not the iterable itself. It's peeling off the next element of the iterable. So Y is not this list. It's not. It would be the element within the list.
Yeah, thank you.
Mm-hmm. All right, I'm getting a time check. So we have time for one more question. So does anyone have a final question?
I have one last question, if you don't mind, Eugene. So you mentioned that map and filter are lazy but not reduced operators or methods. Is there a way for us to check if anything is lazy executable or not, or do we have to just look at documentation?
Well, how you could kind of check, so like documentation definitely helps. But what is the result of a map operation? It's a map object, right? And so like you kind of guess that it's not like it's not a primitive element. It's not like a bool string, float, right? Like it's something different. And you could also get size of the object to see like what the size is, and potentially one way you could check to see if it's like a lazy object is that the size of the object doesn't change despite changing the size of the iterable. So that's like perhaps another heuristic to guess if something is a lazy object or not. Does that answer your question?
Got it. So basically, if it's like constant or like a small number, then it's lazy. Otherwise, you're in trouble.
Yeah, and reduce doesn't give a reduce like what does this thing say? It says map object, right? So like you did type, it'll say map. But like reduce doesn't give a reduce object. It just gives like your accumulator back.
Thank you.
Yep. No problem, no problem. So like we stopped at math filter, but we're only halfway through the notebook. So next time, perhaps we can cover generators, star args, and star quarks, which will then lead to the fancy thing that I promised I would teach you about, which is decorators, and how they apply to not just functions, but any callable. So decorators can apply to even classes and objects. Yeah, you can even apply to object callable. And there's some other helpful libraries. So, but for tonight, we hit our time, and perhaps next time we go through the rest of the notebook. So, Josh, you take it away.
Thanks, Eugene, and thanks for sharing Pragmatic Python with us tonight. I certainly learned a lot, and I'm certainly looking forward to part 2.